he's excited for today's class, but he like, it's not here.
Okay, today we are going to look at BJT characteristics and some BJT parameters or device parameters. So let's, okay, this is an important table. So I'm just going to go over this again. Typically, when we bias a BJT, meaning when we apply DC voltages to set the region of operation, we apply forward bias to the emitter-based junction and reverse bias to the collector-based junction. And what that does is it forces the transistor to operate in a region known as the forward active. Typically, it is also simply known as the active region. Okay, active region. When we compare this to the FET characteristics, this active region in FET would be the saturation region. So it's not the same. Okay, it's not the same. And then if the emitter-based junction and the collector-based junction are both reverse bias, then the transistor is operating in cutoff. When it's cut off, there's minimal current flow, similar to the FET, where the bottom of the graph or the chart, there's minimal current flow or almost zero current flow. Both of those regions, so those regions are known as cutoff. And then if the collector-based junction and the emitter-based junction are both forward bias, then we say that it's operating in saturation. This saturation is different from the FET saturation. Okay, and we'll see that in the next couple of slides. But the important thing here is that in the active region, the BJT is used as an amplifier. It can be used as a voltage, current, and power amplifier. This is a primary mode of operation on which all amplifier circuits are based. Okay, so analog circuit design is primarily when the BJT is operating in the active region. On the other hand, when it's in cutoff and it's in saturation, you have minimal and maximal current flow, respectively. And so when you put both of those regions together, we can use it to create digital logic circuits. When it's cut off, as the name suggests, there is no current flow. So we use that for logic 0. And when it's saturation, that's maximum current flow. We use that for logic high or 1. Okay, so combination of cutoff and saturation allows us to create digital logic circuits with BJTs. Reverse active is, of course, if the exact opposite happens versus forward active. So this region, of course, as you can see, it's marked in red. We don't want the transistor operating in reverse active. No good can come from it, as far as I know. It's just there to show students, what to do if nothing is working in your circuit. It may be that inadvertently the BJT is operating in the reverse active region. And so that is something we don't want. Yes.
What exactly does the reverse active mean? Like what characteristics would we see? Like we accidentally did that out.
Well, this question being asked is about characteristics. It's there on the next slide. The answer is here. So since we're talking about characteristic, I'll come back to the other slide. But the reverse active region is right here. Okay. So this basically shows all 4 quadrants of a common emitter output characteristics. I'll go back to the previous slide in just a minute after we get done with this. So in the characteristics, you can see this region right here is defined as the active region. This is the region of operation if you want to use the BJT as an amplifier. Okay, cutoff is right here at the very bottom. This is, of course, where the current is almost 0, very minimal. And then saturation region is right here to the left. Okay, that's saturation region. And reverse active is, again, when you have No current flow, no voltage drop, nothing works in the transistor. And that would be the reverse active region. And again, at this point, I'd like to remind, FETs and MOSFETs theoretically are symmetrical devices, right? So the drain and the source can be interchanged and would still work. BJTs are not. Just by its very fabrication or manufacturing, BJT is not symmetrical device. Emitter is very heavily doped, is a very small structure. Collector is the largest structure, but it's the lightest doped of all the three structures. Base is very, very thin. So it's not a symmetrical device. So if we do interchange the terminals, it's not going to work for that very reason. Let's expand the characteristics and look at them here. So we have VCE, collector to emitter voltage on the x-axis, output current IC on the y-axis. When we say output characteristic, collector is always the output terminal. Okay, doesn't matter whether it's CE or CB mode, unless of course we're talking about common collector characteristics. But output is always taken from the collector terminal. So collector voltage versus collector current is your output characteristic. Okay. Again, output characteristic, going back to the diode 2. Current as a function of the voltage. How does the current change when the voltage changes? And not just the diode. Doesn't matter what device it is, whether it's a resistor, capacitor, inductor, FET, MOSFET. Characteristics simply means how is the current changing as a function of the voltage. So output characteristics for a BJT is IC versus VCE. You have a set of curves for every input current at the base terminal. So for every value of IB, you have a set of curves, meaning you're changing the output voltage and you're seeing what the response for the collector current is. For the most part, as you can see here, it's almost a flat line. I would say almost a flat line because at the lower input currents, it's flat. But as you go higher up, the slope increases just a little bit. And there is a reason for that. And we will talk about that later. Okay, so you can see that there's a slight slope. For students who did the lab yesterday, or you might have seen some of the transistors. Some of the transistors had output characteristics that had a slope. Several students or several lab groups did not. Okay, so there is slight minimal differences, but there is a small slope as the input current keeps on increasing. Okay. So I'll come back to the transfer characteristic in a bit, but let's talk about biasing modes. What is bias though? Let's give a brief introduction of what bias is. Biasing from diode circuits. It's the constraint placed on the device by the external circuit, right? And then we define the Q point by using the biasing voltages and the biasing currents. So bias typically means the external circuit constraints placed on the device. Okay. Now, we stated that BJT is used as an amplifier, right? Meaning it's taking an incoming signal and it's amplifying. For almost all applications, when we talk about amplification, we are talking about an AC signal that is fed into a BJT circuit, and the BJT circuit amplifies this. You learned about op amps in 113, and then we also did an op amp experiment in this class. Now, op amps are nothing but differential amplifiers created using BJTs. Okay. how does an op amp work in general? Anyone?
By like rounding, like apply BJT or the amp, right? Do you have like those limits?
Exactly. Amplify it. Exactly. So this is something I always like to point out again and again, is that when we talk about op amps, we say op amp has infinite gain. You have inverting and non-inverting configurations of op amps that can have gains of like tens of hundreds, right? So if you apply a 1 volt signal, we'd expect a 100-volt output. But that's not true. Energy cannot be created out of thin air. What an op amp is doing, or what any amplifier is doing, is it's taking the AC input signal and it's combining with the DC source that is present. That DC source is the biasing. That's the biasing voltage. Okay. So in a biasing circuit, we are applying DC source or DC energy, and then the amplifier circuit takes the AC signal, mixes it with the DC source, and then amplifies it. The way I like to explain it is you could take a small AC signal, add it to a DC energy source, and DC energy source could be any value, VDC, and then your output would be an amplified signal. So you could say that the DC level, the flat line, is being given the shape of the AC input signal. Or you could also say the AC input signal is being given the energy from the DC source. Either explanation works. It does not come from thin air. This would be your biasing circuit, provided by your biasing circuit. Okay. And in fundamental electronics classes, biasing is an entire chapter by itself, if you want to go, in depth into it. We won't go too much in depth. We'll look at a few biasing circuits, primarily the most popular one, and which is a 4-resistor bias, which you'll be using for lab next week, and then a couple of other biasing circuits. But anyway, does this make sense to everyone? Right? We have biasing. Biasing is setting the Q point or the operating point of a BJT or a circuit, and it's the external constraint placed on by the external circuit. Yes.
Yes. Why is biasing such like an important thing? Because it seems like if I reverse my BJT,
Mm-hmm.
it just wouldn't work, right? So why does the direction really matter if we only get
So
one region?
good question. So why is biasing important? Right? The gist of why is the biasing important? Well, we want our transistor to operate at a fixed point. If you're using it as an amplifier, going back to your earlier point, if you have an op amp, it might saturate and the top or the bottom of the signal gets clipped off. Clipping would mean distortion. We don't want that, right? So biasing means we want it to operate within the active region. If the AC signal is large enough, or actually it doesn't matter whether it's large or small. If the Q point of the transistor, and I can use this as an example right here, the load line would be something like this. And now we are getting ahead a little bit, but you want the Q point to be somewhere in the middle of this active region. And this setting of the Q point comes from the biasing circuit. If our biasing circuit is not correct, or basically if we design it poorly, then our Q point could be somewhere over here. That could push our transistor into saturation, or if it's somewhere down here, it could push our transistor into cutoff. And that's where biasing is important. Depending on our application, we want a BJT Q point to be either in the middle of the active region or close to saturation or close to cutoff. And that's why it's important. All right, so talked about biasing more, bias and why bias is important. And from that, we can introduce the three modes of operation for a transistor. And that comes from the fact that the transistor has three terminals, and we use one terminal as common for the input side and the output side. So we have three terminals, emitter, collector, and base. If the emitter is common to the input and the output side, then we say that the transistor is operating in the common emitter mode. Okay, it's a common emitter configuration. When we draw a BJT circuit, typically we would draw it like this. Now this is a common emitter configuration, but I will draw the common base and the common collector. And so if I draw it like this, input is on the left and output is on the right. Typically, this is always the way you would see transistor BJT circuits. Okay. Here, base is on the left, collector is up there, and emitter is down below. So you can see the input is between the base and emitter terminals, and the output is collected between the collector and emitter terminals. So emitter is common between the input as well as the output side, and hence the name common emitter configuration. Okay, common emitter configuration. This is also one of the modes that students do in the lab this week. This is also one of the reasons I don't like labs on Tuesdays. Prefer Thursday labs. Okay. And then common base. Again, as the name of the explanation. You have the emitter here. Base is common to both the input and the output side. So input on the left, output on the right. And then far less common is the common collector. So this is CE. CB. And then the common collector this would be the CC mode. Okay. You won't find this in many books. It's hardly ever discussed. Most common is, of course, the CE. It's common and it's the most popular. Several reasons being it has high input impedance, low output impedance. It is easy to bias with a single supply. So you can bias both the input and the output sides with single power supply. And there are a couple of other reasons. These are the three most important ones. So if you're trying to use the BJT as an amplifier, the CE mode is very popular because it has very high input impedance, low output impedance, and you can easily bias it with a single supply. This is also the experiment for next week, CE amplifier. So design of a common emitter amplifier. Okay. All right. Transfer characteristics. Transfer characteristics, again, if you remember, how is the input being transferred to the output? For a BJT, the input is the base emitter voltage, VBE. Output is the collector current. And so transfer characteristics is basically a plot of the output current versus the input voltage. In this case, VBE, the base emitter voltage right here, and the collector current IC right here. And remarkably similar to a PN junction forward characteristic curve right here. PN junction diode and forward bias. If you take that plot and you convert the current into the log scale, as shown here, you obtain a plot that looks like this. Linear, which has a slope of 60 millivolts per decade. 60 millivolts per decade. So for every decade, it drops about 60 millivolts in value. And again, transfer characteristics, basically a plot of IC versus VBE. Similar to the FET, you can obtain this also from this point right here, right? For every IB or VBE value, you have a IC value, right? So if you take this to the left, you can create a plot that looks like this. Excuse me. A couple of other things to note is that in cutoff, IC is very close to zero, right? There is almost minimal input current, IB or VBE. And VCE, when VCE less than equal to VBE, meaning the base emitter junction is not yet fully forward biased, a transistor is more likely than not in saturation. When the transistor is in saturation, typically the VCE values are around 0.2 or 0.3 volts. And we are just talking about silicon transistors. Okay, we won't talk about anything else. Typical values or approximate values for transistors in saturation is 0.2 to 0.3 volts. And if we are talking about the forward active region or just the active region, then the base emitter junction is forward bias. So this is also similar to a forward bias PN junction. So the value for VBE would be about 0.6 or 0.7 volts. If it's cut off, then it's reverse bias. It behaves like an open circuit. All of the voltage will drop across that junction. But if VBE is 0.7, that means it's forward bias. Then we simply look at the collector emitter voltage. And the collector emitter voltage at the output VCE tells us whether the transistor is in cutoff or is in saturation. Okay. And we look at those scenarios also, how to determine the region of operation just by looking at those values. Okay, so one of the most popular circuit models for describing a BJT is by using a current source. If you look at the characteristic, what do we see here? Like the FET, the current is almost constant. If it's constant current, that means it's a current source. And so we can describe the BJT as a voltage controlled current source. We are applying voltage at the input on the base emitter junction, and we can describe it as a voltage controlled current source. And this is, of course, because IC has a near constant value in the active region. So here you have a NPN transistor, and everything we talk about or we discuss with regards to NPN transistors applies equally to PNP transistors, except that the holes and electrons are interchanged and the current directions are reversed and voltage polarities are reversed. But everything works exactly the same. So we have an NPN transistor, 3 currents, base, collector, and emitter current. We can model the base emitter junction as a forward bias diode. Again, we are talking about the active region. So in the active region, base emitter junction is forward bias. Collector junction is always the reverse bias. So the base emitter junction is forward bias. Here's like a PN junction diode. We have a voltage drop across it, and hence VBE is equal to 0.7. That gives us the second model right here. We can replace that PN junction with a constant voltage source of 0.7 volts. Right, 0.7 volts. And then on the output side, we have the collector current IC, and collector current IC is a function of the base current IB. This is the most important relationship. IC is beta IB, right? Beta is a transistor parameter that is determined during fabrication. It's the ratio of the output current to the input current. IB is the input, IC is the output. And IB itself is a function of the applied voltage at the base, VBE, right? And so we can describe IC as a voltage controlled current source. Okay, voltage controlled current source. And because it's semiconductor PN junction, it is highly temperature dependent. That's why we have all these experiments in the lab with temperature dependencies. And so temperature is a big consideration when you're designing. For normal circuits, if you're just using for everyday consumer applications, it does not matter much. If it's extreme environments, perhaps military, perhaps in a very hot environment or a very cold environment, perhaps you might be doing some research in the Arctic or the Antarctic regions or somewhere in a hot desert, then you need electronics that can work at those temperature ranges. And devices would be fabricated to meet those considerations. For the most part, we'll simply take VT as standard room temperature, 25 millivolts. 25.8, but we'll stick with 25 since the book sticks with 25. All right, so that's the forward active region. And then, of course, the IE current sinks everything. IC plus IB gives you IE. All right, how are we doing on time? 15 minutes left. Okay, example. Forward active region. Some values are given to us, and we are asked to determine the other values. So what is given to us? IS is given to us, the saturation current, as 10 raised to minus 16 amps. Alpha is given to us as 0.95. Alpha is the ratio of the collector current to the emitter current, as a reminder. And again, since it's forward active mode, we can put a subscript of F in there. And then VCC is given 5 volts. and the input current is given 100 microamps. Okay. This is, of course, a very simple biasing circuit. We are applying the power supplies directly to the transistor, the BJT, without any current limiting resistors. And then we are asked to find the currents flowing through the circuit and the voltages present in the circuit. So we already have IB given to us. We need to find IC. We need to find IE. And then we need to find VBE and VBC. VBC, base to collector voltage. Now, if certain values are not provided, you can always make assumptions. As an engineer, you will be doing that a lot. You'll make assumptions, you will use multiple models. You might try one model, see if it works for your circuit. If it doesn't, you will try something else. Okay, that's why we have multiple models, because no single model can accurately describe all circuits. Okay, so if these are not given, you can simply assume. VT is not given, we will assume VT. Let's assume VT as 25 millivolts. Okay. Also, right now we already know that we are discussing forward active or the active region, right? If it's not given, typically my go-to analysis, I would always choose active mode first, and then I would analyze the circuit, see if it matches my assumptions. If it works, it works. If it doesn't, then I go back and make a different assumption. Okay, there's only 3 modes of operation: active, cutoff, or saturation. Okay, and so I'm going to assume that this is an active region of operation. And if it is active region of operation, that means that VBE is a forward bias PN junction. Base emitter junction is forward bias. And so VBE would be approximately equal to 0.7 volts. We will find the exact value at the, as we progress through the problem. But for the beginning analysis, we'll assume 0.7 volts. Okay. All right. So VBE would be positive because current IB is flowing into the transistor. It's flowing into the transistor. It's an NPN transistor. So it's going from P to N, PN junction, right? So it's forward biasing the PN junction. Assume VB is 0.7. Then I can find VC. VC in this case, measured with respect to the emitter terminal, is equal to VCC, which is 5 volts. Right? Collector voltage, 5 volts. And so from here, I can then find VBC. VBC would be the difference between and that would be equal to 0.7 minus 5 gives me minus 4.3 volts. Minus 4.3 volts. Base to collector is negative, which means it is forward bias, reverse bias. It's a reverse bias, right? Which is what we would want in an active region of operation. Okay, so then we can find IC. IC is beta times IB. Beta is not given to us, but alpha is. So we can write alpha over 1 minus alpha times IB. And you plug in the values. 0.95 divided by 1 minus 0.95 times 100 microamps. This, by the way, comes out to be 19 times 0.0001. And that gives me IC as 1.9 milliamps. Okay. 19, by the way, is a very low value for a real life transistor. Typically, beta values are in the hundreds. Okay. From the IC values and the IB values, we can find the emitter current IE. The equation for IE is beta plus 1 times IB. Yes, you are right. 19 plus 1, 20 times. Yeah, and just write. Wait, 1, 2, 1 extra 0. Okay. So that would be 2. And now we are in a position to actually calculate the value for VBE. Okay. VBE can be determined from the equation IC over IS. And so that would be 0.025, 25 millivolts log of IC is 1.9 milliamps, and reverse saturation current 10 is to minus 16. And that gives us an exact value of VB. It's 0.764 volts. Not too far from our assumption. Okay, not too far from our assumption. So our assumption at the beginning was 0.7, and our calculated value turns out to be 0.764. And one final value remains is VBC. So calculated value for VBC would be VB minus VC. VB is just VBE. So 0.764 minus 5 is minus 4.24 volts. Which again, not too far from 4.3. Okay, so 4.24 volts. Let's see if we can get through the next example. Okay, forward active example 2. We have a PN junction. This time we have a BJT, and this time we have biasing resistors at the collector and the emitter. We also have dual power supplies at VCC plus 9, and you have VEE minus 9. Base is connected to ground. Okay, base is connected to ground. We are provided values for beta forward 50, beta reverse as 1. And we're going to assume or make assumptions again that this is in the active region of operation. Therefore, we can assume VBE is 0.7. We are asked to find the Q point for this biasing circuit. Okay, we are asked to find the Q point for this biasing circuit. So for a diode, the Q point was ID and VD. What is the Q point for a BJT? VCE, IC. I see. It's always the collector. Remember? So if it's the Q point, we want to find values for IC and VCE. Okay, IC and VCE. Okay, we have 5 minutes left. If you have to leave at 9, you can feel free to leave at 9. Okay, so we're going to apply KVL. So here we have the equivalent model, the forward active model, forward bias diode, VBE, collector current as a function of IB, beta F times IB, and VCC plus 9 volts, VE minus 9 volts. So we can apply KVL at the input loop, and we can also apply KVL at the output loop. By the way, these applying KVL at the input and the output side is how you would primarily generate your equations for pretty much all circuits. Okay. Oftentimes you'd also apply KCL, again, depending on the model and depending on what we need to find. But for the most part, when we begin analysis, or when I typically begin analysis, I always begin by applying KVL. So on the input side, we have these voltages, and on the output side, we have these voltages, right? So if you apply KVL on the input side, KVL at input loop, I can write VBE base to emitter voltage plus the voltage drop across the RE resistor, which is right here. It should actually be RE, emitter resistor RE. Okay, so it'll be IERE, IERE, and then minus VEE is equal to 0. Okay, currents flowing in the downward direction. So voltage drop is plus at the top, minus at the bottom. So that gives me 0.7 plus 8200 IE, and then minus 9 volts is equal to 0. Therefore, IE can be written as 8.3 divided by 8200, 1.01 milliamps. IE is 1.01 milliamps. Okay, again, KVL on the input side, you have 3 voltages, VBE, the voltage drop across the emitter resistor, RE, and then the source, VEE, 3 voltages. And from there, we can find IE. Now, from the expression for IE, we can find IB. We can write IE is beta plus 1 times IB. And so I can write IB is IE over beta plus 1, which gives me 1.02 times 10 raised to minus 3 divided by 50 plus 1. It gives me IB of 19.8 microamps, which seems about right because IE and IC are typically in milliamps and IB is typically in microamps. If you obtain a slightly higher value, 10 raised to minus 6, 10 raised to minus 5 is reasonable. even 10 raised to minus 4 on occasion, but IB would not be more than that. IB is typically in microamps. A quick verification check is if IB is not in the 10 raised to minus 5 or 10 raised to minus 6 range, then it's probably not correct, and there's an error somewhere in your calculations. And of course, IE is the largest of all three currents. Okay. All right. So then from IB, we can find IC. So beta times IB. And that's 50 times 19.8 times 10 raised to minus 6. That turns out to be 0.99 milliamps, which makes sense because IC again should be very close to IE, but slightly less than that. Okay, so if IE, emitter current, is 1.01, IC cannot be more than that. It cannot be far less than that either. It's usually within a couple of milliamps. So 0.99 makes sense. And now we are ready to apply KVL on the output side. Output loop. And then we can write VCE is equal to VCC minus ICRC minus or minus VBE, so plus VBE. Then I can write VCE is equal to 9 volts minus 0.99, 10 raised to minus 3 into RC, which is 4,300 ohms plus 0.7. Okay. And therefore VCE is 5.44 volts. 5.44 volts. Therefore, my Q point is 0.99 milliamps and 5.44 volts. Okay. There were a few other things I wanted to cover, but I guess that will have to wait until Friday. So we'll end class here today, and I will see you all on Friday. What was the